All right, let's get right into it. Today, we are tackling one of the biggest, most fascinating ideas in all of AI. How does a machine go from just recognizing things to actually creating them? We're taking a tour of deep generative models, the algorithms that are learning to generate our world, and in the process, maybe even understand it.
And this quote from the deep learning textbook, our main source today, really just nails it. This isn't just about making cool, realistic pictures. It's about a much grander ambition, building a framework for understanding reality itself. That's the real quest here.
So, here's our game plan. We'll kick things off with the big promise of generative AI. Then we'll dive into this really elegant, physics-inspired idea of using energy to think about probability. From there, we'll crack open a classic model, the Boltzmann machine, before jumping into the modern world of GANs and diffusion models. And finally, we'll wrap it all up, connecting it back to that ultimate goal of understanding.
For the longest time, if you were doing machine learning, you were probably doing recognition. You were classifying things. But the cutting edge has really shifted to something way more ambitious, and that's creation.
Okay, so here's the fundamental difference. A discriminative model, that's your classic classifier. It learns to draw a line in the sand between, say, pictures of cats and pictures of dogs. It finds the boundary. But a generative model is not interested in the boundary. It's trying to learn the very essence of catness or dogness. So well, in fact, that it can dream up a totally new picture of a cat from scratch. It's learning the whole distribution of the data, the entire landscape, not just a dividing line.
So how on earth do you learn an entire data distribution? Well, one of the earliest and most beautiful ideas actually borrows a concept straight from physics, energy. And this gives us this amazing family of models called energy-based models.
I want you to imagine a kind of landscape of all possibilities. In this landscape, things that are really unlikely, like a TV screen full of random static, are way up high. They're high energy, unstable states. But the things that are plausible, like a clear picture of a human face, they're down in the valleys. They're low energy, stable, preferred states. The whole point of the model is to learn the shape of this landscape.
And that's pretty much the formal definition right there. An energy-based model doesn't try to spit out a probability number directly. Nope. Instead, it just assigns an energy score to everything, and the rule is dead simple. The lower the energy, the higher the probability. So training is all about learning to push the energy down for things that look real and crank the energy way up for everything else.
All right, to make this a little more concrete, let's look at one of the originals, a classic energy-based model called the Restricted Boltzmann Machine, or RBM. It's just a perfect blueprint for how these things work.
The setup is actually super simple. You've got one layer of visible units, that's your data, like the pixels in an image. Then you've got a hidden layer, and its job is to learn the abstract features behind the data. But the real genius is in the name, the restriction. Visible units only talk to hidden units. There are zero connections between units in the same layer. And that little rule changes everything.
Now, don't get too hung up on the math here. Just look at what's in the equation. The energy of any given state depends on a few things the model has to learn. B and C are biases for the two layers. But the really important part is that W. That's the weight matrix that captures how strongly the visible and hidden units are connected to each other. The entire training process is just about fiddling with these knobs to get the energy landscape right.
And this is why that restriction is so incredibly clever. Because there are no connections inside a layer, if I show you an image on the visible layer, you can figure out the state of every single hidden unit completely independently, all at the same time. And it works in reverse, too. This conditional independence is what makes the whole thing possible to compute efficiently. It's a brilliant computational shortcut.
Okay, let's hit the fast-forward button, because from these foundational ideas, the field just completely exploded. Energy-based models are critical to understand, but the modern era is really defined by a whole new set of architectures that have pushed generative AI into the stratosphere. Today, the scene is dominated by a few major players, and we're going to focus on two of the most important ones, the famous Generative Adversarial Networks, or GANs, and the models that are really state-of-the-art right now, diffusion models.
So, GANs are built on this amazing concept of a two-player game. You have a generator, think of it as a master art forger trying to create a perfect fake. And then you have a discriminator, who's like a detective trying to tell the fakes from the real deal. They train together, locked in this adversarial battle. The forger gets better, which forces the detective to get smarter. And this constant one-upmanship pushes both of them to incredible levels of skill.
But here's where GANs get really weird and interesting. They can produce these stunningly realistic images, right? But as our source material points out, they can do that while technically assigning zero probability to the actual real-world data. How?
Well, they aren't learning a smooth probability landscape. They're just learning to trace out this very thin, complex surface of what looks real. And this is exactly why they're so hard to train. The two networks are constantly trying to find a stable balance, a Nash equilibrium, but they often just end up chasing each other around in circles, never quite settling down.
And that instability is a big reason why the field has moved towards the current champion, diffusion models. The idea here is just so intuitive and way more stable. Step 1. You take a perfect image and you just destroy it. You add a little bit of noise, then a little more, until it's pure static. Step 2. You train a massive neural network to learn how to undo that process, to take the static and, step by step, clean it up back into a perfect image. Once it's trained, you can just give it random noise and it will denoise it into a brand new, incredibly high-quality sample. So let's just step back for a second. We've gone from energy models to adversarial games to this process of denoising. What does it all really mean? Where is all this headed?
Well, it all circles back to our big theme. The act of generating something is an incredibly powerful way to learn. You can't create a believable human face out of thin air unless you've implicitly learned about eyes and noses and hair and lighting and symmetry, all of it. By learning to generate, these models are forced to build a rich internal map of how our world is put together.
And this final quote really drives home the utility of it all. A well-trained generative model isn't just a toy for making images. It's a powerful tool for inference. It can fill in missing pieces of data. And it creates these amazing hierarchical representations. It learns simple things like edges and colors at the bottom and combines them into complex concepts like cat or car at the top.
And that leaves us with this final, massive question. The ability to generate is deeply, deeply tied to the ability to understand. So as these models get better and better at recreating the world we see and hear, they are undeniably on a path towards a new kind of understanding. The question for us is no longer if they'll get there, but what that understanding will actually look like.